Okay, just a quick announcement regarding your midterm. So I have finished designing it. I just have to make sure that it'll take me between 20 to 30 minutes to solve. I think it will. So I'll release a formal statement about the midterm on Wednesday, but it will be 4 questions. And it should take you roughly half an hour to do. Some questions may take a little longer than others. Like there's one question which should take you like 10 minutes to do, or maybe even 5. It should be very quick. But like in terms of your time, but it's 4 questions, and it's about 110 minutes to 120 minutes or so. So it should be about 2 hours. So I'm in the middle of designing that, but I just wanted to give you a quick lowdown. So it's 4 questions. Should take you roughly half an hour to do for each, maybe a little less, maybe a little more, but in total it should span about 2 hours for you to complete. Okay, I'll release a formal statement on Wednesday once I finalize everything. So I'll let you know on Wednesday through the videos, and I'll also release a formal statement through email as well, and put it on the D12 website just to let you know. Okay. All right. So today we're going to finalize amplitude modulation. We're going to cover a really cool topic, something that's something that you can relate to. We're going to talk about radio frequency receivers. So especially in your car systems, especially if you tune into the AM part of the radio frequencies like FAN 590 or AM 640. We're going to talk about one of the earliest models to receive AM signals, which is called the superheterodyne receiver, and then there are other technologies that are based off of the superheterodyne principle, and I'll talk about those as well. So we're going to talk about radio frequency receivers today. Okay. So radio frequency or RF receivers are the foundation of all communication systems, which makes sense. This is actually the superheterodyne receiver. Most of all was actually used during the first 2 world wars, so to communicate between different camps, especially the encryption also is a different story. I'm not going to talk about that, but the method to transmit signals through amplitude modulation was used throughout the first 2 world wars using the superheterodyne receiver. So we're going to go in a lot of depth with regards to how exactly these work, and then how exactly you would, the technologies of the math and the engineering principles behind how radio frequency receivers work. So we're going to talk about superheterodyne first off. It's one of the most fundamental receiver technologies that exists. And then you have the holodyne or zero IF. IF means intermediate frequency. I'll talk about that later. And low IF receiver. So these next 2 technologies are based off of the superheterodyne principle, which I'll talk about later. So before I get into radio frequency receivers, I'm going to talk about the superheterodyne receiver now. But a topic that I'm going to talk about is what's known as frequency division multiplexing. So FDM. What exactly is that? Well, the basis is that you've got a very very large channel where you can squeeze a lot of different message signals inside the channel. So you can think of it as different AM radio stations that are broadcasting over the air. The air would be the channel, and each station has a dedicated carrier frequency that they use to transmit their signals over the air. Okay, so what you can do is you can basically squeeze all these signals onto one large channel that has a very large bandwidth, and then what you can do is you can just, if you want to tune into the station that you desire, you just put a bandpass filter around the station that you want to tune into, and filter everything else out so you can listen to that particular station that you want. Okay, so suppose we have in this let's go with just 3 signals for now. Suppose we have 3 different signals that are shown by the following 3 spectra. All right. And then what we're going to do is we're going to use a modulator, whether it's double sideband suppressed carrier or amplitude modulation or whatever you want, but some modulator, if you will. And we're going to modulate these with different carrier frequencies. We're going to choose the frequencies such that we want to squeeze all these spectra together so that they don't overlap in such a way where you can squeeze a bandpass filter to filter out the right signal or the right carrier, the right station that you want to listen to, and you filter the rest out. Okay, so we're going to assume that each of these signals have the same bandwidth for now. Okay, that's actually common practice. If you take a look at AM radio stations, they assume that there's a common, there's the same bandwidth that each station embodies, and then we're going to modulate them at different frequencies, make sure that none of these signals overlap, and we're going to push them over to the channel. Okay, so notice that each of these frequencies are called, this is a first carrier frequency, the second carrier frequency, and the third carrier frequency. You're modulating, or you're choosing frequencies in such a way that you're putting them on the channel so that they don't overlap. So if you actually add these all up, they will simply just be all 3 of them existing on the same, in the same signal over the same channel. So using frequency division multiplexing, we can transmit multiple signals over the same channel. right? So that actually makes sense, because you want to everyone can just use one channel to save a lot of money, and then you just transmit over the same channel, different radio stations with different carrier frequencies. So each signal has its own frequency band. So for example, this would be one frequency band, so this is a frequency band. Okay, this is another frequency band, and so on and so forth. So, this is another frequency band, and so on and so forth. So each of them have a particular carrier frequency that they're transmitting at, and then they occupy a certain width in channel space, all right? So carrier frequencies are selected so that the modulated signal spectra do not interfere with, with messages that are adjacent or near the ones that you're looking at. Okay, so that kind of makes sense, right? Instead of transmitting just one signal, you want to transmit a bunch of signals, and you just apply a bandpass filter to the one that you want to listen to, and then you filter the rest out, all right? Okay, so the condition is that you want to make sure that each of these frequencies are, you have some particular order. It doesn't have to be, in this case we've chosen such that the first carrier frequency is less than the carrier frequency, and then the third carrier frequency is greater than the other two. That's fine. And you want to make sure that the difference between the two carrier frequencies is twice the bandwidth, right? So this between here and here makes sense. It's twice the bandwidth. So between here and here is B, and here is B. So you want to make sure that this and this are satisfied. So this, this is the difference between the two, and then you also have the difference between the two here as well, right? You want to make sure that these are satisfied to make sure that there's no overlap. Okay, so you can think of it as, remember, when you're tuning into the radio station, you can think of, in this case, you are changing where the center of the bandpass filter is, so that you are filtering out the right frequency or the right station or carrier frequency you want to listen to. So you can think of it as adjusting your bandpass filter to get the right signal that you want. Okay. All right. Oops. I'll go here. Okay. So if you want to receive a single station or a single channel, this is probably what you'd want to do. First, you want to use a bandpass filter to, in this case, let's choose the second carrier frequency for now. So you choose a bandpass filter that's centered around the station you want to listen to, and then you want to make sure that the width of the bandpass filter captures the signal exactly. And then, you put a bandpass filter here, and remember, this is for positive only. The negative we're going to assume is symmetric, all right? So this is positive only for now, all right? So, okay, so let's say this is 0, I guess. All right. So you want to apply a bandpass filter on the signal you want to extract, and then you do a demodulator so that you can convert this down to baseband signal, right? Because right now this is bandpass. You want to bring it down to its baseband equivalent so you can listen to what the actual message signal was. Okay, so let's see here. So bring back down to baseband. That's the point of the demodulator, right? So bring back down to baseband signal. That's the point of the demodulator. Okay? And then once you take that signal out, you just put it out to an audio amplifier or some transducer that'll convert your message signal into an audio signal, and then you go ahead and listen to whatever station you're tuned to. Okay? So the purpose of the bandpass filter is to isolate the signal you want to receive. So you want to choose which station you want to choose which station you want to listen to, put a bandpass filter, surround that particular station or whatever carrier frequency that station is transmitting, right? So for example, if you're listening to FAN 590, their carrier frequency is 590 kilohertz. If you want to listen to AM 640, their carrier frequency is 640. So whenever you are tuning into your radio station, whatever radio station you're tuning into, that is the carrier frequency that they're transmitting over the air. And then you use a bandpass filter to figure out which station you want to listen to, and you want to isolate all the other signals, right? So the purpose of the bandpass filter is to not only receive the signal that you want to listen to, but you also want to filter out all the signals that you don't want to listen to. You just want to listen to one station at a time, right? You don't want to listen to other stations that are interfering with the station that you want to listen to. Okay? So the pass band is compatible. So there's two ways you can do it. If you want to do double sideband, right, you want to make sure that the bandpass filter spans between, the plus minus the bandwidth of the message, right? So in this case here, this is embodying this particular scenario, okay? You can also transmit using single sideband if you wish. That's totally fine. But in this case, this here is doing double sideband express carrier. There's also a possibility where you can transmit through single sideband if you wish. But currently, I believe we're doing double sideband at the moment, at least for AM signals. I believe that's what's going on currently. But you can do either one. You can do DSB or SSB, whichever one you wish. Okay. So you have the capability to receive different channels. As I talked about, all you got to do is just have a bandpass filter that's tunable so that you're just making sure that the center of the bandpass filter is, right smack dab in the middle of the carrier frequency that you want to filter out. Okay, so this is what is known as a tunable RF stage, where basically what you're doing is, this is, okay, so a tunable RF stage or tunable radio frequency stage, this is a tunable bandpass filter. Okay, so you're centered, sorry, can't write, centered at the station's carrier frequency you want to listen to, okay? All right, so it's a tunable bandpass filter. So you want to slide it around, or you want to choose a carrier frequency that is of the desired signal that you want to extract out. Okay, so that's how you want to receive different channels, right? So you just have to have a bandpass filter that's adjustable so that you can select out the signal that you want to receive, demodulate it, and go ahead and put it through an audio speaker to listen to what it sounds like. Okay, so in this case, this is a double sideband suppressed carrier because it spans between minus and plus, whatever the bandwidth of that signal would be. Okay. Okay, so this is another situation where if you wanted to listen to, not this carrier frequency, but this one over here, right? All you're doing is you're just centering the bandpass filter so that you get this signal instead, and you want to make sure that it spans between plus and minus B, which is, so twice the bandwidth. You want to make sure that the bandpass filter is twice the bandwidth of your signal, and you want to get that particular message out, demodulate it, put it through an audio speaker, and then go ahead. So we're going to do something like this for your very last lab. So I'll talk about that later on, before the end of class. But the last lab that you'll be dealing with, you're going to deal with MATLAB and Simulink to actually listen to radio signals over the air, and you're actually going to go ahead and demodulate actual radio signals, and you can actually listen to them over the speaker that's in the lab. So the last lab will be to actually demodulate and listen to actual radio signals that are being transmitted over the air. So that's going to be a pretty cool lab. Okay, so you may notice that there might be a slight problem with this, okay? Notice that each of these signals are so squeezed together that there's very little room for tolerance. This means that you're going to have to design a bandpass filter that is very close to ideal, if not ideal itself, and that's very impossible to do, if not very expensive, okay? So there's got to be some other way to deal with this where, so in theory, this totally works. Design a bandpass filter, put it around the station you want to listen to, and filter out the rest of your signals. But if you practically, you want to squeeze as many signals together as possible. So there's very little room to have a little bit of tolerance. So you'd have to design an ideal bandpass filter to get the message that you want, right? And that's going to be a little hard to do, right? So this approach will work, but the design and implementation of a tunable RF stage with high sensitivity, high gain over a wide range of frequencies is difficult and expensive. The reason why is because, right? Let's see here. So if you want to filter it out like this, requires a very an ideal bandpass filter, if not close to ideal. And this results in a lot of money. It costs a lot of money to do that. No one's going to buy your product if it's going to, it's going to cost like $1,000 or $2,000 because of that close to ideal bandpass filter. You got to have something cheap that'll receive radio signals, right? So this may not work. So there's got to be a different way to do something that will perform, in the same performance, but make it as cheap as possible. So there's got to be another way to do it, okay? So what we have so far is we've got a bunch of signals that are over your channel, right? And then we have a tunable RF stage. So this is a tunable bandpass filter. So that means that you have your, you're centering your bandpass filter around the particular station you want to listen to. So there's another trick we can try instead. Why don't we leave the bandpass filter fixed at some frequency, but then we will shift what we'll do is we'll mix or we'll modulate the actual signals that are coming through the air so that they will go down to where the actual bandpass filter is centered. So instead of taking a bandpass filter and centering it around the frequency that you want to filter, why don't you manipulate the signals so that you'll shift the spectra around so that they'll fit into a bandpass filter that's fixed in frequency. And that's actually a lot more cheaper to do, and that's what we're actually going to do instead, okay? So instead, what we'll do is we will implement, we'll implement the electronics, or we'll implement the logic so that you shift around the actual signals that are being, transmitted over the air, but we'll have a fixed bandpass filter. And that's actually a lot cheaper to do, because what you can do is you can make it such that you can have the best bandpass filter as possible, but then as soon as you make it tunable, that's what drives up the price a lot. So you can make the bandpass filter as close as ideal as possible, but at a fixed frequency, and then that way it'll drive the cost down even more. Okay, so this frequency, this fixed frequency, this is what is known as an intermediate frequency. And I'll talk about this in a little bit, but that's what F sub IF is. So what you want to do is you want to take your signals that are being modulated over the air, and then you want to put them through some sort of modulator such that it translates these signals, or translates all the frequencies down to a frequency that is centered at this bandpass filter that is fixed. And then you can go ahead and do the logic that we talked about before. Okay, so that's actually a lot more cheaper to do. Okay, so a fixed RF stage, or in this case, RF stage means bandpass filter, so I'm going to use that interchangeably. So when people talk about an RF stage or a radio frequency stage, what they really mean is a bandpass filter. Okay, so a fixed bandpass filter can have all of your desired filtering and amplification properties, and it's actually a lot cheaper to make it fixed at one frequency, and you can make it as best as possible, so you don't have to translate this bandpass filter around. Okay, so the objective is, instead of having a tunable bandpass filter, you want to frequency shift all the signals that are coming that are modulated so that the desired one fits into the range of your fixed bandpass filter, and then you go ahead and demodulate that, put it through your audio amplifier, and then you're good to go. Okay, so that's what we want to do now. So you want to frequency shift the incoming signal so that the channel we want to receive matches the pass band of the fixed RF stage. So, for example, let's say we have this signal that's being shifted, and what you want to do is you want to, let's say, for example, you want to make this one, you want to shift it in such a way that this gets moved over so that it fits within the, so that the this frequency now transforms into the intermediate frequency, and then you can go ahead and filter that if you wish. Okay? And I'll talk about how exactly you do that very soon. So just bear with me for a moment. So, this is, let's see here. So, let's see. All right. So, for example, let's say, this is the frequency that, for example, this would be the station I want to filter out, right? You just mix the appropriate frequency in. And then, you would, if you wanted to get, the first one, for example, you choose the right frequency so that when you shift it, you'll get the first one and it fits into the actual bandpass filter. So something like that too. So you're shifting all the frequencies in such a way that the channel or the station that you want to listen to will fit exactly where your bandpass filter is designed or specified. Okay? So this is what is known as frequency shifting or mixing. So this is all you're doing here is you're taking your signal, which is already modulated, and you're multiplying by another cos. Okay? So I'm just going to do a little bit of math for you so you can see what I'm talking about. So let me just make a new page. Okay? So let's assume DSBSC for now. Okay, so let's say we have some signal that is modulated at some carrier. Okay, so usually, before, when you wanted to demodulate, right? If you wanted to demodulate, you would just multiply by a cosine that has the same carrier frequency. So you got your DSBSC signal that's coming in, right? And then you multiply by a cosine of the same frequency. Right, and then you apply a low pass filter, and then you're good to go, right? So that'll be the output. All right, so that's what you would do. Now, what you're doing now is that you're not multiplying by a cosine of the same frequency. You're going to multiply by a cosine of another frequency, and the ramifications of that are actually quite significant. So let's say, you've got your double sidebands coming in, okay? And instead of a carrier frequency omega c, we're going to multiply by another carrier frequency, which we'll call omega L sub O. And this is what's known as a local oscillator frequency. So it's not the same frequency as the carrier, but it's something that is generated on the receiving side that is something different. Okay? So what exactly happens here? Well, this becomes m of t, and then cosine of omega c t, right? Cosine of omega LOT, right? And then if you remember, there's a trigonometric rule where if you multiply two cosines together that are different, right? Right, what happens? You get half, and then you get cosine of a minus b, and then plus a half cosine of a plus b. So as you see here, what's happening is that this is what is known as frequency mixing, because when you actually multiply two cosines together that are different frequencies, you're going to generate two new cosines where you have one that is 1 subtract the other and one that is 1 plus. So in this case, what's going to happen is that you're going to get half of, so we get half m of t, and then this becomes cosine, oh, darn, Went all the way to the end. Let's see, where am I? Yeah, there we go, sorry. Cosine, and then you have omega c minus omega LO t, and then plus half m of t cos omega c plus. Okay, so that's what's coming. That's what's here now. Okay, so that's what's known as frequency mixing, where when you multiply by two different frequencies, you're going to generate two new cosines, where one is the difference and one is the addition. So what this is doing is that generates two new modulated signals centered at omega c and then plus minus omega LO. Okay, so I'll just make one more page here so I can show you, just to make sure that we're on the right track. Okay, so if I take this here, the Fourier transform, not M of J mix, sorry. So let's call this, I guess, y of t, all right? So the Fourier transform at this output, right? Remember, when you're multiplying by a cosine, when you take the Fourier transform, you're performing modulation, right? So this becomes half m of, and then you have omega minus, sorry, omega c, sorry. You have omega minus, and then omega c minus omega LO, right? And then plus half. No, sorry, it's minus again. Okay, so that's what's happening here. So you get copies of your spectrum, but they're centered at two different frequencies. Okay, so you can call this omega 1, and this is omega 2. Okay, so that's what's known as frequency mixing, where you take a cosine and you multiply it, you take your modulated signal, you multiply by another cosine of a different frequency, and then what outputs is that you have copies of the spectra centered at two different frequencies. And you can verify that if you make the local oscillation equal to omega c, then you'll notice that the first one cancels out, so you just get m over omega, which we talked about, and then this becomes omega minus 2 omega c. So you can use this to verify that if you set your local oscillator frequency to be the carrier itself, this is just your standard demodulation for your double sideband suppress carrier. Okay, so that's the point that I wanted to address. So what comes in, the output has two copies of your spectra at plus minus, omega c plus minus, and then omega LO, which is the local oscillator frequency. So that's what I wanted to bring up. So definitions. So heterodyning. So this is what I talked about is also known as heterodyning. So this is also known as frequency mixing. Heterodyning also means that if, I can do this. So what this means specifically is doing this. Okay, so this is what is known as heterodyning. What you are doing is that you are taking your original modulated signal and then you are translating them or modulating or heterodyning them so that they appear in different parts of the spectrum instead. Okay, so the reason why you want to do this frequency mixing so that it allows us to take your modulated signal, right, and then you want to shift it so that the desired spectrum or the desired signal that you want to listen to is at a certain frequency that is tuned to where the bandpass filter would be, and then you go ahead and do the rest of the logic that we talked about before. Okay, so this is what is known as an intermediate frequency. So this where you want to do here is you want to take the station or take the carrier frequency. Take the desired and convert to FIF through heterodyning. Okay, so that's what we want to do. Okay, so if your carrier frequency is within a range, so usually for AM signals, they broadcast between AM 540 to AM 1600 kilohertz. So that actually makes sense. Okay, and the intermediate frequency is fixed. We want that to stay put because we want to design a system that is cheap. Okay, so how you do that is actually very simple. So you have to use what is known as, so what you could do is you would make the local oscillator variable. Okay, so I'll talk about why you need to do this, but how this will work is if you want to tune into the frequency that you want to listen to, you have to make sure that you adjust your oscillator so that when you actually do the frequency mixing, it'll take your desired station and bring it down to where the intermediate frequency is centered at, so you can actually go ahead and filter it out and take a look at, take a look at the signal that's being filtered out, or take a look at the signal that's remaining. Okay, so you need to make sure that you have a local oscillator that is variable so that you can achieve what I talked about here. So how exactly does that work? Okay, so yeah, variable. Okay, so we have a variable, local oscillator, and then this here is what is known as an intermediate frequency amplifier. So intermediate frequency. Amplifier. This is basically, what this basically means in layman's terms. It is your fixed bandpass filter that is centered at your intermediate frequency that will filter out the right signal for you. So the IF amplifier is really your fixed bandpass filter. So the tunable RF stage is your tunable bandpass filter, which is going to be very expensive to create. But we could, and then you have an IF amplifier or an intermediate frequency stage that is a fixed bandpass filter. So the difference between the tunable and the IF is that the IF has a fixed bandpass frequency, or fixed center frequency with, that is centered at the intermediate frequency. All right? Okay, come on. Okay. So here are some very popular intermediate frequencies. So for AM radio, the intermediate frequency is actually 455 kilohertz. For FM broadcast radio, you go to the higher, you go into the megahertz, so it's 10.7 megahertz. For radar, you actually go even higher, which is about 30 to 60 megahertz, and for TV, the intermediate frequency is 43.75. So you can think of TV as kind of the same thing, where you're transmitting all these channels over the air. It doesn't exist now because we're going digital, but how TV signals worked is that you transmit it over the air. You had each channel that occupies its own frequency band, and then you want to tune into the right channel such that you want to isolate out the carrier frequency that is desired for that channel, and then you go ahead and do the rest of the logic that I talked about. And then satellite receiver is actually 70 megahertz. So that's actually, so as you start going modern and modern, the carrier frequencies start to get higher and higher. Okay, so this is the diagram that we've talked about that actually performs our demodulation of our signal, and then we want to listen to it in the output. So let's actually go through this diagram from beginning to end. So this input, this is your FDM signal, your frequency division multiplex, your frequency division multiplex signal. Right, so you've got a bunch of signals that are modulated at different carrier frequencies, and then let's say that we want to listen to the desired frequency that is centered at f of c. So this is your desired carrier frequency that you want to listen to. This is the desired frequency that you want to isolate out from the rest. Okay? And then you have your local oscillator here, and the reason why this is here is because it'll allow your carrier frequency to be translated to where the intermediate frequency is. You filter that out, and then you go ahead and do the rest of the logic. So let's assume for the moment that we want to make sure that the desired carrier frequency you want to listen to is called f of c. Okay? And then once we put it through your lot oscillator here, you're basically taking your multiplex signal, your frequency divided multiplex signal, and you are multiplying by your local oscillator. So you're translating all the frequencies by a desired amount. Okay? So at this point, okay, what's going to happen is that, remember, you have a cosine that's coming in here, then you have a cosine that's coming here. So so what you're going to have is that you're going to have, there's two different possibilities. Okay? So remember, when you're drawing out the spectrum, so this here is the positive side, right? And this is the negative side. Because remember, the spectrum we're going to assume is symmetric, the signals are real. So when you actually go ahead and do your frequency mixing, you've got the positive side where you have two copies at plus minus the local oscillator with the carrier, and then you have it on the negative side where you have plus minus as well. So you have two copies on the positive side, two copies on the negative side, right, that we talked about before. So in superheterodyning, what you want to do is you want to what's known as downconvert. So what it means that downconverting is that you're assuming that the carrier frequency is much higher than the intermediate frequency. So what you want to do is you want to take that carrier frequency and shift everything down so that the carrier frequency becomes the intermediate frequency instead. So that's what it means by downconverting. So what you want to do is you want to change FC into FLO such that the local oscillator frequency is much higher than the carrier. Okay? Or in other words, you would say that the intermediate frequency is larger than that as well. You can do that as well. Okay? So what this implies is that assuming that the local oscillator is, for the moment, is much is larger than your carrier, what you're doing is that you basically take your local oscillator frequency. If you subtract it by the carrier, you will get the intermediate frequency. So that's what's actually happening here. So you have your carrier frequency, you put it through your local oscillator, and then you mix it so that you generate this new frequency, and that is your intermediate frequency. So let me just do a couple of numerical examples just to be sure that we're on the right track here. Okay, so we're going to first define your local oscillator frequency. So for example, let's say I want to tune into a station that is at 600 kilohertz. So when I tune into my radio station, the AM dial, I'm going to tune it to 600. Okay, and then we're going to assume that the signal has a bandwidth of 10 kilohertz. So this means that this spans between 590 to 610. So that is the bandwidth. So that is the pass band of the signal. All right. Okay. Okay. So this local oscillator frequency, you are setting it such that when you perform your mixing, you will make it such that one of the copies of the spectra will be centered at 455. Okay. So if I define my local oscillator frequency such that, so you're just going to take your carrier and then you add it with your intermediate frequency. So 600, and then we're going to define the intermediate frequency to be 455 because that's what it is for AM. And then you have 1055. Okay? So then what's going to happen now is that when you put it, so at this point here, okay, when you put it through this point, we're going to generate two new frequencies. Okay? You're going to generate two new frequencies at FC minus FLO and FC plus FLO. Okay? So in this case, we get, let's see, so FC, so this becomes, what's going on here? So FC, so this becomes 600, subtract 1055, okay, and then 600 plus 1055. So this becomes minus 455, and this becomes, let's see here, this becomes 1655. Now the negative here is not alarming at all. Negative doesn't matter. The reason why is because, remember, if you're using a cosine, remember cosine is an even signal. So if you have cos of negative x, it's the same as cos of positive x. Okay, so negative doesn't matter. Right, because cosine of minus x is equal to cosine of plus x. It's an even signal, right? Okay, so negative doesn't matter. So this is an even signal. But the point is that you're generating two new frequencies at 455 and 1655. So then, because your intermediate frequency, your bandpass filter is centered at 455, we will finally be able to get a copy of the signal that you want to, demodulate and listen to your, listen at the output, even though we specified the desired carrier frequency is 600. So you're taking your desired carrier frequency 600, translating it down to 455, and then putting it through your electronics so that you can actually listen to the signal that's centered at 600. Okay? All right. Okay, so here's a little bit of a diagram. This is a little bit of a, here are some diagrams, or here's some pictures that represent each stage of this superheterodyne receiver. So we've got an input signal coming in where it's centered at 600. So 600 is the station that we want to listen to, right? And remember, the bandwidth is 10. So remember, this is in kilohertz. So this would be 610, and this is 590, and this is minus 610, and this is minus 590. Okay, so let's go ahead. Okay, so we have this. Let's take a look at what the local oscillator would look like. So when you take a look at the spectra for the local oscillator, remember, this is f of c plus f of I at the intermediate frequency. So this becomes 1055. Okay, so what you're going to do now is when you decide to take a look at the spectra, remember what you're doing is you're generating two new copies such that you're adding the two frequencies. So you got 1055 plus 600. And then you're subtracting, so you get 600 subtract 1055, or 1055 subtract 600, doesn't matter because it's even, right? So at the output, this is what we get, right? So we have two new frequencies, a 455 and 1655. And remember, we want to be able to filter this out. Remember, this is the intermediate frequency. So we want to filter everything else out, but then center our bandpass filter at where the intermediate frequency is. So after the output of the amplifier, the IF stage, the copies at 1655 will obviously go away, right? So that's what happens. right? So this is the the intermediate this is the intermediate frequency amplifier. It's basically a bandpass filter, and I'll address. Let's assume ideal for now, but I'll talk about the realizable case later. But let's just assume ideal cases for now. So you put a bandpass filter centered at 455 within the span of the bandwidth of the signal, all right? And then you get this as the output, which is great. And then when you demodulate, what's going to happen is that you're making these signals go so that it's centered at your baseband, which is centered at 0, right? So that's what's going to happen next, right? And then this is your new signal, right? So notice that, this is the original message, but there's going to be inevitably some gain factored into it, whether it's a half or some other gain, depending on what modulation scheme you use. And then you're going to take your signal here, and then you're going to put it out through an audio amplifier, and then you're going to listen to whatever that signal would be. So that's good, right? So all you have to do is, if you want to tune into the station that you want, all you got to do is set your local oscillator to be the desired carrier frequency that you want to listen to, added with the intermediate frequency, and then you go ahead and do your process here. Okay, so that's the next slide that I'm going to show you next. So if you want to listen to another radio station, let's say instead of 600, you want to go to 1,000 instead. So all you have to do is set this so that it becomes f of c plus f of if. So assuming that our intermediate frequency is still 455, you want to set this so that it's 1,000 plus 45, so then it's 1455. So then when you go ahead and when you go ahead and mix this, then you're going to have f of c minus f of low and f of c plus. So that one of them will become 455, and the other one is something that is bigger that we don't care about. Okay? So that's what we're talking about here. So instead of changing the electronics, all you're doing is changing the carrier frequency, the local oscillator frequency, so that it tunes into the station that you want. So you adjust the local oscillator frequency so that it's the carrier, the one that you want to listen to, and then you add it with your intermediate frequency so that when you push it down through the pipeline, the desired signal, which is centered at 1,000, gets converted down to 455, and then you go ahead and push it through your electronics and you get to listen to your radio station. Okay? So what's important is that there are no further changes to the demodulation structure. All you're doing is changing the local oscillator frequency. The rest of the electronics, the audio amplifier, the demodulator, the intermediate frequency amplifier, all that stays the same. So that is a cheap system, because making a bandpass filter that is tunable, it can get a bit expensive, especially if it's ideal or close to ideal or very, very good. Okay, so that's very important. So if you want to listen to another radio station, you just have to change the local oscillator frequency so that you get this guy here. Okay, so you have to make sure that this relationship holds. All right. Okay, so a superheterodyne receiver is set up with a frequency adjustable local oscillator, all right, as well as a well-designed intermediate frequency stage. So we can this is actually realizable, and I'll talk about how realizable this is in a minute, but assume for now that it's ideal, okay? So your bandpass filter is realizable, and it's good quality, and it's not tunable, which makes it a little cheaper, okay? So if you want to listen to your favorite radio station, let's say it's centered at 600 kilohertz, all you have to do is add 455 to f of c. In this case, this is your intermediate frequency. You add 455 to your intermediate frequency, and you make that your local oscillator. You go ahead and multiply this with your frequency divided multiplex signal coming in. You go ahead and push it through your signal. You push it through your system, and then you can listen to it at the output. So I guess you can pour a cup of coffee, and then you can sit back and listen to your radio station that's centered at 600 kilohertz. But there's a slight problem with this, and I'll talk about this right now. So what's going to happen is that not only will you be able to listen to your station at 600 kilohertz, you're going to also hear remnants of another station, and that station is centered at 1510 kilohertz. So what's going to happen is that if you don't design this properly with the system that you have set up right now, not only you're going to have your signal, or you're going to hear the signal at 600 kilohertz at the output, you're also going to hear remnants of your signal that is centered at 1510 in the output as well. And why exactly is that? Why is that exactly happening? Why is it so that you have your 600 and then you also have a copy of 1510 as well? Why is that happening? What's going on here? So what is happening? Did we use something? Did we use the wrong trig identities, or did we use something wrong with the Fourier transform? What exactly is happening? Why is it happening? Okay, so here's your potential hazard. All right, so we made adjustments for our station broadcasting at 600 kilohertz. So you've designed your system in such a way where you're shifting your frequencies down to so that the station that you want to listen to is going to be centered at 455. So this is the diagram we talked about before, right? So you have your local oscillator frequency, which is centered at, you know, omega f of c plus f of IF, right? And then f of c here is 600 kilohertz, and your intermediate frequency is 455, okay? So you're heterodyning, or you're mixing the frequencies, you're shifting it. And then you generate these, you know, these two copies. And then these are the ones that you want. Okay? Sorry. Okay. So now the other station at 1510, this is the reason why it's happening. So at 1510 kilohertz, right? Remember this signal, you know, you have a bunch of spectra that is occupying this particular signal, right? So remember, not only are you shifting the 600, you're also shifting what is occupied at 1510 as well. Remember, this signal consists of multiple stations. So what you're doing is you're frequency shifting it such that the desired one that you want is at 600. But at 1510, if you decide to do the same technique, right, if you're doing the heterodyning, what's happening here is that you're generating two new frequencies, right? You have FC minus FLO and FC plus. No, sorry, FLO, it's FIF. Yeah, FC of, sorry, FLO, is you have two of them, right? Okay, so in this case here, let's assume that this is 1055. So you have, not 1055, you have 1510. So 1510 minus, you know, 1055, right? This is 455, and this is 1510 plus, which is 2565. So you see what's going on here? So remember, we're designing it in such a way where you are translating everything so that, you know, you're filtering at a 455. But at 1510, when you're doing the heterodyning, what's happening is that 1510 will also be translated down to 455. So that's the reason why you have two different stations that are occupying the same frequency band. Because what you're doing is you're taking your frequency divided multiplex signal and you're shifting everything by, the local oscillator frequency. So that at 1510, when you actually do the heterodyning, remember, you're adding and subtracting by 1055, which is what the local oscillator is. So at 1510, it's also going to go down to 455 too. So at 600, you go up to 455, but then at 1510, you're also going down as well. So that's the reason why you have two different signals that are occupying the same frequency band at 455. It's just naturally how the heterodyning works. Because remember, you're taking any frequency and you're plus minusing whatever the center is. So you take your center and then you plus minus, the local oscillator, and one of them unfortunately still happens to be a 455. So how exactly do you compute this number? How exactly do you get this? It's actually very simple. All you're doing is you're taking your carrier frequency and you're actually just adding twice the intermediate frequency to get that. And that actually works out like that. So both stations get down converted to the intermediate frequency, and that's interference. So what's happening is that you'll have two different signals that are going to be at the same, that are occupying the same space within the, the confines of your intermediate frequency, and that's not good. Okay, so your local oscillator down converts the carrier to your intermediate frequency, and it also down converts a second signal. This is what is known as your image signal. Okay, and the frequency that this happens at, the image frequency, is what's known. So this is what's known as the image frequency. So in this case, for your carrier at 600 kilohertz, right, and your intermediate frequency at 455, okay, the image frequency is at 1510, okay, and this actually is defined as your carrier plus twice the intermediate frequency, and that actually makes sense, okay. So if you actually do the heterodyning, if you did cosine of, let me see here, it was, let's see, so, this is the desired carrier frequency that we want, okay, and then your cosine of f of c plus 2if. Okay, let me see here what's going on. Actually, let me just double check. Let me see if I got that right. 2if, yes. Okay, good. Okay, so this is the, let me see here. Actually, sorry, let me see. So this is, okay, so you have your desired carrier frequency here, right? So this is what happens after you put it through. And then once you do this with twice the intermediate frequency, okay, and remember, this is defined as, what was it? This is f of c plus f of if, okay? So if you actually decide to mix these up, what's going to happen is that, let me see here. When you actually do the frequency mixing, what's going to happen is that you will generate another cosine such that it becomes cosine of f of IF, and that's the reason why it passes through. Okay, so you have this, and then when you multiply by a frequency of twice this, so if you actually go ahead and do the actual mixing, like if you do plus and minus, you will see that you'll get one of the components that are centered at this, and that's actually not what we want. Okay? Okay. So this is what's known as the image frequency. So what we probably want to do is when you go ahead and design, your bandpass filter, right? When you filter out the signal that you want to make sure that the image frequency gets rejected as well. So you want to make a bandpass filter such that you get the actual frequency that you want. So you're going to have to introduce a bandpass filter at the beginning. So have a bandpass filter before you actually go ahead and start mixing, such that you have your carrier frequency, and then you want to make it reject frequencies at twice the image frequency. Okay, so what you want to do first is you want to first figure out what the image frequency is. So you figure out what the local oscillator frequency is, which is what we have here. Okay, and then the image frequency is basically just the carrier and then twice the intermediate frequency. Okay, so there's two different situations here. The situation that we deal with is usually this one here. Okay. So that's the one we usually deal with. But there's a situation where the local oscillator frequency may be less than the carrier. If that's the case, you need to subtract instead of add in order to get the local oscillator, so that when you actually do the heterodyning, you'll get the intermediate frequency of that particular signal. You'll take your signal and modulate it down to where the intermediate frequency would be. So this is a situation where it's greater. If it's greater, then you simply add. If it's less, then you simply subtract. So those are the only two differences. But we usually deal with this one. That's the one we usually deal with. Okay. Okay, so you know what? I'll take a break now, and we'll come back in about 10 minutes, and I'll finish up this topic. All right. So let's take a little break. Before I continue.